Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Mr. Manideep Gupta, Assistant Professor from Department of Aeronautical Engineering, MLR Institute of Technology. Today, the topic which we are going to cover under this lecture series is combustion instability. Combustion instability is a very important topic to be discussed in propulsion systems. Okay. So the propulsion system generates thrust when you burn propellant in the combustion chamber. But the thrust produced should be uniform and constant. Then only we can move our vehicle in the required path. If the thrust generated by the combustion system or the propulsion system is not constant, if it is unstable, then we cannot, the mission profile cannot be achieved as our requirements. That's why combustion instability is very important to study in propulsion systems. So the combustion instability deals with the different phenomenon or different criteria that leads to the combustion instability or improper combustion or improper or uniform, which affects the uniform combustion process in the thrust chambers. Okay, so today the topic is combustion instability. So coming to the overview of today's presentation, today we are going to cover the combustion instability in rockets with examples, and also we discuss about bulk and wave mode of combustion instabilities. Next we will discuss modeling of bulk mode of instability in solid propellant rocket motor and liquid propellant rocket motors. So these are the topics to be covered in this lecture series. Coming to the combustion instability. What is combustion instability? So the combustion instability refers to the undesirable oscillations in pressures, thrust or heat release inside the rocket combustion chamber. Suppose if you take a combustion chamber like this, if you take a rocket like this, okay, consider this is the nozzle, this is the nozzle. Okay, the thrust produces the gases eject from the nozzle in this direction. If the thrust or the pressure, okay, these gases ejects from the nozzle due to the pressure developed in the combustion chamber. Okay, and thrust produces here at the nozzle exit, and the energy will be released in the combustion chamber. Right. If these parameters are not constant, if the pressure in the combustion chamber is not constant, or the thrust produced by the rocket is not constant, if it is oscillating, if the parameters like pressure, thrust and heat release in the combustion chamber are oscillating, then that is called combustion instability. So combustion instability is nothing but the oscillations in pressure, thrust and heat release inside the rocket combustion chamber. So these oscillations, so these pressure fluctuations, pressure increases, decreases in the combustion chamber. So the thrust also increases, decreases based upon the pressure in the chamber, and the thrust will not be uniform. So which is nothing but combustion instability. Okay. So these oscillations can be low frequency oscillations. Whatever the pressure or thrust oscillations, these can be low frequency oscillations, which is called as chugging, or high frequency oscillations, which is called as screeching or buzzing. And these oscillations, these fluctuations in the pressure and thrust can cause severe engine damage or sometimes complete collapse of engine. Okay, complete failure of the engine, and it will cause the severe damage to the structure of a engine components. Can cause catastrophic engine failure also. It can cause catastrophic engine failure due to vibration and thermal stresses. So when the pressure fluctuations, then the pressure increases, decreases, it will create vibrations, and the thermal stresses on the propellant tank, the stresses that is developed on the propellant tank increases, decreases, stress oscillations. So the strength of the material also will get affect. The chamber strength will get affect. So because of that, catastrophic engine failure can occur. Okay, this leads to the reduced performance and inefficiencies. Whatever the combustion instability, that leads to a reduced performance. The performance of the engine will reduce if there is combustion instability. Next, the combustion instability limits the engine design envelope and operational stability. So, this also affects the engine design envelope and operational stability. So, controlling of the vehicle also affects with the combustion instabilities, because the pressure is fluctuating, thrust is not constant. So, we do not know at what is the path it is going to follow. Like for that, because of that, the operation stability will be very difficult if combustion stability exists in the engine. So, we have to avoid combustion instability as much as possible. Coming to the real world examples. So, if you take a F1 engine, which is used in Saturn V Apollo program, so there is a problem arises due to the combustion instability, that is severe high frequency instability during development. In the development phase itself, they faced this combustion instability problem. Severe high frequency oscillations occurred in the F1 engine while in developing phase. So what happened? So the effect due to these high frequency oscillations on the engine is combustion chamber pressure oscillations. So caused hard starts. So starting is not easy, and injector damage. It is damaging the injector of the combustion chamber, and it risked the explosive failure. Even the engine also failed. Okay, explosion happens because of this high frequency oscillations. Okay, so the solution they found for this combustion instability, high frequency instability, is they reduced the injector plate. Okay, they redesigned the injector plate. They redesigned the injector combustion like fuel, propellant and oxidizer injector plate with baffles and acoustic cavities. Extensive test on fixed approach to eliminate the instability. So what they did is they modified the injector plate used in that F1 engine. They modified the injector plate so that and also they used baffles. The baffles divided the combustion regions into small regions so that they can easily control the combustion instability that is avoided in the F1 engine. So this is one example of combustion instability in F1 engine. So because of that, because of using this redesigning injector plate and baffles, the stabilized and the combustion process become stabilized and became one of the most powerful, reliable engines ever flown, the F1 engine for Apollo program. Just because of injector plate design, combustion instability arose and complete engine failure occurred. So after redesigning the injector plate, it became the most powerful engine. Next, another example is SpaceX Raptor engine. SpaceX Raptor engine, which is used in the Starship program. The problem arises is their high frequency combustion instability, right? So here the combustion instability observed during the early hot fire test. So during the early hot fire test, they found the combustion instability. The process of combustion is not uniform. It is not constant. Fluctuating flames. Okay. So the effect, the cause of this is high chamber pressure and use of methane and LOX in a full flow staged combustion cycle. So why this combustion instability arises here in the SpaceX Raptor engine is because of high chamber pressures. They redesigned high pressure chambers and they used methane LOX in the full flow stage combustion cycle, which is sensitive to pressure fluctuations. The methane LOX combination is very sensitive. So the combustion process is very proactive. So the pressure fluctuations are more. Instantly the pressure varies. Okay. So the solution they found is they refined the injector and combustion chamber design. So they have gone through the high pressure chambers. So they redesigned the combustion chamber, and also they redesigned the injector and leveraged the real time data and iterative testing with rapid development cycles. They changed this injector and combustion chamber designs. So the result is improved engine stability and performance occurs across the multiple generations like Raptor 1 to Raptor 2. So here the problem arises due to the high pressure design, the combustion chamber is designed for high pressure, and also the propellants methane and LOX. So methane propellant system, that is injector. Even they redesigned injector and combustion chamber so that combustion instability is avoided. So this is another example of a real-time world. Next, Indian cryogenic upper stage, GSLV. In GSLV also, we, while developing this, we observed the combustion instability problems. So Indian cryogenic upper stage in the GSLV, the problem is in the early launches. In the early launches, engine underperformance. The performance is not up to the mark, possibly linked to combustion instability or related issue like improper mixing. So engine performance is not up to the mark. The engine performance is dropped. So the reason is combustion instability. The combustion is not uniform. Okay, combustion is not uniform because of improper mixing of fuel and oxidizer, or the flow rate which you are maintaining in the combustion chamber. So these are the reasons for underperformance of the engine in the cryogenic upper stage in the GSLV. So the solution they found is they improved the propellant feed system. So improper mixing, right? The reason they found is improper mixing. So they redesigned the propellant feed system and injector design and thermal insulation. Even they modified the thermal insulation. They focused on controlled ignition and steady combustion. So finally, they have avoided the combustion instability, and we are experiencing the successful GSLV operations every day. So the result is cryogenic stage now reliably flies in GSLV MK2 and MK3. So this is the examples in combustion instability happens in the real engines which we have developed, and the problems they found and the solutions developed for the combustion instabilities. So now you may got understood how the combustion instability is important in the performance of an engine. So coming to the types of combustion instability. So there are two types: bulk mode of combustion instability and wave mode of combustion instability, right? Bulk mode of combustion instability and wave mode of combustion instability. So the bulk mode of combustion instability comes to volumetric mode. So if you take the combustion chamber like this, the total combustion chamber, the pressure in the combustion chamber uniformly changes everywhere. The pressure in the total combustion chamber varies uniformly as a unison. Okay, here the pressure rises, here also rises. Every place the pressure rises uniformly like a single volume. Then that type of combustion instability is called bulk mode of combustion instability. Okay, so it is also called a volumetric mode. It is also called a piston mode or acoustic monopole. Okay, it involves uniform pressure oscillations throughout the combustion chamber. If the pressure is 10 megapascal here also the 10 megapascal MPa. If here the pressure drops to 5 mega MPa, then here also it will drops to 5 megapascal. Just for example, I am saying, understanding purpose. The real pressures will not be this much. It is very less. What I said is okay. So the pressure changes uniformly throughout the combustion chamber. Then that type of combustion instability is called bulk mode of instability. So the entire bulk of the gases expands and contracts together like a breathing motion. That is about the bulk mode of instability. Characteristics. Okay, coming to the characteristics of bulk mode, how this bulk mode of instability behaves. Okay, here the oscillation coming to the properties like a oscillation pattern, how the oscillations, it is high frequency, low frequency, it is a uniform or not, wave mode or not. Next, frequency range, the reason of bulk mode instabilities, what are the effects that happens due to the bulk mode of instability. Those are going to discuss here. Coming to the oscillation pattern, here the entire chamber pressure rises and falls uniformly. The entire pressure rises and falls uniformly in the bulk mode of instability. Next, frequency ranges, it is a low frequency oscillations. The frequency oscillations frequency in the bulk mode of instability is low frequency. It will be between 10 to 200 hertz. 10 to 200 hertz. The causes of bulk mode instability. General causes of bulk mode instabilities are coupling between propellant feed system and combustion chamber. So the interaction between the propellant feed system and the combustion chamber. If you take here, injector will be there, and after that combustion chamber will be here, and the propellant feed lines will come here like this from the propellant tanks. Okay, so here the interaction between the fuel feeding system and the combustion chamber, that the coupling that will leads to the bulk mode of combustion instability, and also the delay between the feedback system, the combustion delay, right? The coupling between propellant feed system and combustion chamber will cause the bulk mode of instability, which is an example of chugging. So the effects due to this combustion instability is it can damage the pumps, and also it can damage the valves, feed lines due to the oscillating flow rates. The flow fluctuates, right? So it will affect the pumps, valves and feed system. So the bulk mode of instability mainly affects the feed system, propellant. It affects the propellant feed system. But if the pressure fluctuations are more, then sometimes it will also leads to the total engine failure also. So the chugging in early liquid propellant engines where fuel flow oscillates cause combustion chamber pressure rise and fall in a synchronization. So next is wave mode of combustion instability. Okay, wave mode of combustion instability, right? Second one. The wave mode of combustion instability is also called as standing wave modes. It is also called as standing wave modes. If you take the pressure fluctuations, if you consider the pressure and this is along the combustion chamber length, then the pressure fluctuates like a wave. Like a wave. Some point in the same combustion chamber, at some point the pressure, point 1 the pressure will be different, point 2 the pressure will be different, and point 3 the pressure will be different. It fluctuates at particular position like a wave. Okay, the pressure fluctuations move from the combustion chamber, from the fuel injector to the end of the nozzle. So then that type of combustion instability is called wave mode of combustion instability. So the instability where the pressure wave resonate inside the chamber forming standing waves. Okay, divided into longitudinal and transverse and also tangential modes based on direction of wave oscillations. The oscillation based upon the direction of wave oscillations, we can divide this wave modes into different types like a longitudinal, transverse and tangential modes. So these mode can amplify rapidly. So in this wave mode of instability, the oscillation can increase rapidly, so which is very dangerous. So can cause a localized heating. It will also cause injector damage and complete engine failure happens in wave mode of instability. So the control strategies. Okay, coming to the bulk mode, damping via accumulator volumes, stable propellant feeding designs and slow valve actuation. This will decrease the bulk mode of instability. Coming to the wave mode of combustion instability, Helmholtz resonators, baffles using baffles and injector tuning, chamber geometry optimizations, which leads to the wave mode of combustion, decrease in wave mode of combustion instability. Okay, so this is about bulk mode of instability and wave mode of instability. So now we'll discuss the characteristics and about this longitudinal, transverse and tangential wave mode of instability. Coming to the longitudinal wave mode of instability, the oscillations along the length of the chamber. The oscillations happens along the length of the chamber. The frequency will be 1 to 10 kilohertz, high frequency. The visual pattern is like a pipe organ tube. Next, coming to the transverse oscillation, the wave move side to side across the chamber. Side to side across the chamber. Mid to high frequency cause sidewall vibrations. This will create sidewall vibrations. Okay. Next, tangential oscillations around the circumference. Okay, if I take the oscillations around the circumference. So these are high frequency oscillations often dominated in annular chambers. Generally, in annular combustion chambers, we can experience this tangential wave mode of instability. So this is along the length. Longitudinal means along the length of the chamber. Transverse means across the chamber, side to side, which will damage the side walls. Coming to the tangential oscillation, which will lead to damage the annular, like a annular chamber. It happens in annular chambers. It also affects the walls and other injector parts. So this is about wave mode of combustion instability. Next, coming to the bulk mode instability in liquid propellant rockets. Bulk mode of instability in liquid propellant rockets. So generally the reason is coupling between the feed system dynamics, combustion response and combustion chamber volume. So these are the reasons we discussed, right? So the feed system dynamic means it involves with the design of pipes, valves and also the pumps which you are using in the feed system. And the combustion response. So how fast the combustion process is going on. The time of combustion of propellants, that is a combustion response, and the pressure buildup in the combustion chamber, that comes under combustion response. The sensitivity of combustion pressure flow changes. If I change the mass flow rate of the fuel in the combustion chamber, there will be some change in the pressure. So how effectively the time taken for this pressure buildup or pressure drop is nothing but the combustion response. Okay, next, combustion chamber volume, like acting like a spring mass dynamic system. So these are all causes in the bulk mode of combustion instability in liquid propellant rocket motor. And the frequency can be calculated with the help of F is equal to 1 by 2 pi gamma PC by rho L into L into Vc. Here the frequency of oscillations is equal to gamma is the specific heat ratio, PC is the chamber pressure, combustion chamber pressure, rho L is the liquid density, L is the length of the chamber and Vc is the volume of the chamber. So the pressure in the chamber, the volume of the chamber, length of the chamber. So these are all important. Okay, L is a characteristic feed system length. Next, liquid propellant density, chamber pressure and chamber volume Vc. Next, solid propellant. Coming to the bulk mode of instability in solid propellant rocket motor. So the mass generation rate from solid grain burning couples with the chamber pressures. So the burning of solid propellant leads to develop pressure in the combustion chamber. So that will leads to that will generate the bulk mode of instability if the combustion process is not uniform. Okay, the combustion surface increases. Sometimes it can be progressive burning. Sometimes in some propellant grains it can be regressive burning or neutral burning happens. So when the surface area changes rapidly, then these oscillations can occur. The bulk mode of oscillations can occur in solid propellant rocket motor. The oscillation arises when burn rate responds to pressure, reinforces chamber pressure changes. Okay, natural frequency for chugging in solid motors can be calculated here with the help of this formula. F is equal to 1 by 2 pi into under root of gamma P AT by rho S A N A B V C. What are these parameters? AT is the throat area. A and N are the burn rate constants. This A and N are the burn rate constants. That will depends upon the type of propellant grain, the type of propellant grain, whether it is a increasing, regressive, progressive or neutral, based upon this A and N changes. Next, AB is a burning surface area. AB is a burning surface area. This is burning surface area, and rho S is the solid propellant density, the propellant density. Okay, P is the pressure in the chamber. Coming to the bulk mode of instability, in a bulk mode of instability, modeling involves in dynamic system analysis. We have to go through the mass flow rate and the pressure fluctuations. The pressure fluctuations depends upon the mass flow rate of the propellant we are supplying into the chamber, and combustion response modeling. So how fast the combustion process, the response due to the combustion in the combustion process after injecting the propellant, how fast the pressure is building in the combustion chamber, and also the feedback system, how fast the feedback system is sensing the changes in the parameters in the combustion chamber. That also leads to the combustion helps in bulk mode of instability. and also coupling between combustion chamber and fluid mechanics. So necessary for both these are necessary for both liquid and solid rockets, ensuring the engine stability performance. So these are the major parameters to be concentrated to avoid the bulk mode of instability in liquid and solid propellant rocket motors. One is mass flow rate, pressure, combustion response modeling, and also combustion, the relation between the combustion process and fluid mechanics, coupling between the feed system and combustion chamber. Okay, here you can see different types of instability, like bulk mode of instabilities. Here the mass flow rate m dot p. Okay, you can see m dot p is the mass flow rate of the propellant which we are supplying through the injectors. Okay, CD is the coefficient of discharge of the injector, A naught is the area of cross section, rho is the density of the propellant, and PNG here is the injector pressure. PNG is the INJ is the injector pressure, the pressure at which the propellants are injecting in the combustion chamber. Next, PC is the chamber pressure. Here the PC is the chamber pressure, the pressure developed in the chamber. So here you can see the injection pressure will be different, the pressure developed in the chamber is different, and m dot n is the mass flow rate of the gases at the throat. Okay, so this is the formula, this is equation for mass flow rate, propellant mass flow rate. Okay, m dot p. It depends upon the difference in injection pressure and the chamber pressure. Okay, m dot p can be here. From this we can if you write the equation for mass flow rate of the gases, then it will be m dot n is equal to PCAT by C star. We already know this. Mass flow rate of the gases is PCAT by C star. We have already developed this equation in the previous lectures. So here you can see this. So if you use that formula of propellant mass flow rate, m dot p is equal to CD A naught into 2 rho P INJ minus PC. If you use this equation, and if you, based on that, if you control the pressure in the in the combustion chamber at different propellant injections pressures. Okay, first I am taking the example of injection pressure is 7.5 megapascal. The injection pressure is 7.5 megapascal. I am considering I want to maintain a pressure of 5 megapascal. I want to maintain a 5 megapascal in the combustion chamber. Okay, right. So here you can see the two graphs. On the x-axis, on the y-axis, you can see the pressure in the megapascal, and on the x-axis you can see the time, the pressure fluctuation with respect to the time. Here in the second graph also, in the second graph you can see the mass flow rate of the propellant m dot p, and with respect to the time on the x-axis. Okay, if you see here the pressure fluctuations up to this here, up to A, the pressure fluctuation, there is no pressure fluctuations. It is constant. The pressure is constant up to point A. At from point A, you can see there is a down. The pressure decreases and increases, decreases and increases. Okay, if you observe here, the pressure is fluctuating between these two lines. Okay, that is 5.5 and 4.5. Okay, the pressure is fluctuating between 5.5 and 4.5. You can see the oscillations, how the pressure is oscillating with respect to time. So the oscillations are constant. The oscillation is constant. The frequency is constant. So it is a constant amplitude oscillation. We can call this as constant amplitude oscillations. Constant amplitude oscillations. Right. Now we will design this. How we can see based upon that formula how it is developed can be explained here. And next you can see the another type of bulk mode of instability here. Here you can see now in the previous we have maintained how much 7.5 megapascal, right? Now I have changed my injection pressure to the 7 megapascal. Okay, when you use 7.5 megapascal, the pressure fluctuation is constant. But here when I increasing the injection decreasing the injection pressure to 7 megapascal, you can see the pressure fluctuations here. Up to this point, the pressure is constant. Here I have changed. There is a small combustion instability occurred. Okay, what happens? So here the pressure is decreased to 4.5. The pressure is decreased to 4.5, right? So when the pressure is decreased, so I have to maintain 5 megapascal, right? So what I do? I will provide more propellant. So here you can see the mass flow rate of the propellant with respect to time. So here exactly here the combustion instability happened and the pressure drops to 4.5. So what they did according to the formula, the actuator did is the actuator has increased the mass flow rate from m dot bar to 1.12 times of m dot. So the mass flow rate is increased here because the pressure is decreased from 5 to 4.5. Okay, so what happens when you increase the mass flow rate? Definitely the energy released in the combustion increases, so the pressure will be increased in the chamber. But how much extent it is increasing? See here. So this whatever the propellant increased here, it has taken some time. This is the delay time. Whatever this time taken, this is the combustion delay. Okay, during this time delta T, whatever the excess propellant that is burned and released the energy. Okay, because of that released energy, the pressure has increased to 5.59. But actually, how much we need? We need only 5. But the pressure is increased to 5.59. So, what is our next step? The actuator, what is the next step to be done by actuator? We have to decrease the pressure from 5.59 to 5. So, again, the actuator will decrease the mass flow rate, m dot. Okay, so m dot is decreased here because the chamber pressure is increased to 5.59 there. So m dot is decreased, mass flow rate is decreased to 0.84 times of, so 0.84%, 84 times of mass flow rate. Then it has taken some delta T time to react. So because of that, mass flow rate is decreased, right? So the pressure has to decrease. But to which point? The pressure has to decrease to, the pressure has to decrease from 5.59 to 5 only. That is our requirement. But what happens? The pressure has decreased from 5.59 to 4.2. The pressure has decreased to 4.2. Here initially it is decreased to 4.5. Next time it is decreased to 4.2. It is more. The lower value is increasing. Okay. And here again the mass flow rate increases. We have to increase mass flow rate to increase the pressure. Again mass flow rate is increased to 1.18 times. In the previous one we have increased 1.12 times. Now it is increased to 1.18. More propellant flow rate is increased more to overcome this high difference. 5 minus 4.5 is only 0.5. 5 minus 4.2 is 0.8. So to increase the 0.8 pressure, we increase the propellant flow rate to 1.18 times of m dot. So again the pressure is increased, but now it is not reached to 5, but it has reached to 5.92 again. So what you can observe here is initially it is 4.5, 5.9, after that 5.92, here this 4.52 to 4.2. So the pressure difference, okay, the pressure difference is increasing. Here this is the pressure difference and you can see this is the pressure difference. So the pressure difference is increasing with respect to time. The pressure oscillations is increasing with respect to time when you are maintaining 7 megapascal injection pressure. Okay, this type of wave combustion instability is called increasing amplitude modes. Increasing amplitude mode. Okay, so in the previous one you can see when the pressure is maintained 7.5 megapascal, automatically the pressure is decreasing and increasing, but the oscillation range is constant. So here the difference what we changed in the combustion design, everything is same. The chamber pressure which we are maintained also same 5 megapascal in both cases, but the difference is injection pressure. So injection pressure is playing very important role in combustion instability. If you are maintaining 7.5, the combustion oscillation, the combustion instability is continuing, but the oscillations are not increasing or not reducing. When you are going to 7 megapascal, the pressure fluctuations are increasing with respect to time. But what is our requirement while designing the combustion chamber? Whatever the combustion instability develops, that has to be decreased. Suppose even sometimes combustion instability occurs, but the pressure fluctuations should decrease time to time, and finally it should mitigate. Okay, that is our requirement. So what we do? So we have to adjust the injection pressure such that the pressure fluctuations should decrease with respect to time. So that will be explained in the next case. Here initially 7.5 the pressure is constant. if you maintain 7 megapascal, the pressure is increasing. The pressure fluctuations is increasing. So what the next step is, we have increased the pressure more than 7.5, that is 9 megapascal. 9 megapascal. Then you can observe what happens to pressure here. See here, initially the pressure is constant up to this point, and there is small pressure fluctuation happens, that the pressure decreases to 4.5. So we substitute these pressure changes in the equation. Okay, m dot p equation we have gone through in the earlier slide. So because of this decreasing the chamber pressure, the mass flow rate is increased to 1.061. This mass flow rate is calculated based upon the formula. This mass flow rate is calculated with the formula m dot p is equal to CD A naught into under root 2 rho Ping minus Pc. By using this equation, this mass flow rate is calculated. This will be calculated by the actuator only. Now we don't calculate it. We give the input to the actuator to calculate the mass flow rate according to the pressure fluctuations in the chamber with the sensing data, and the mass actuator will increase and decrease the mass flow rate. So actuator will calculate based upon the formula, and it increases the mass flow rate to 1.061 m dot, 1.061 times of the normal mass flow rate. So because of this, there is a time delta t. It will take so till delta t the pressure is constant. Here the pressure is constant during this combustion chamber till Tc. So the reaction happens now. The pressure is increased because of 1.061. So 0.061 propellant is extra propellant is provided. Because of that, the pressure is increased to 5.3. Okay, again we substitute this chamber pressure and the injection pressures in the equation, and the actuator again finds the next propellant feed rate to be maintained. This is the next propellant feed rate maintained to decrease the pressure. So it is decreased to 0.962 m dot. So again the chamber pressure decreased to 4.8. Initially it is 4.5. Next it is 4.8. So it is nearer to the 5. Next again mass flow rate increases here. Again mass flow rate is increased here. You can see the increase in the pressure, but it is not 5.3. It is less than 5.3. So it is 5.12. So almost near to the 5. Okay. Next again the mass flow rate has decreased here. So again the pressure will decrease, but it is less than 4.8. So it can be 4.9. So finally what happens? The oscillations decreases like this, and the oscillations will decrease. Completely it will mitigate. So this is about the decaying amplitude oscillations. The amplitude is decreasing. With respect to time. And finally after this time, suppose if here from this again the oscillations are decreasing, and here the oscillations are 0. So this is the time. This is the time taken for the combustion chamber to mitigate the oscillations. So after that again the combustion process will be constant, and you will get the uniform thrust. So this is decaying amplitude motions in the bulk mode of instabilities. Okay, this all happens because of the injection pressure. This injection pressure, if you change the injection pressure, if you maintain 9 megapascal, automatically whatever the instability maintains in the combustion chamber, automatically it will mitigate automatically, and combustion stability occurs. But if you maintain 7 megapascal, whatever the combustion stability arised, that will be maintained continuously until you take a separate action. Okay, if you maintain 7.5 megapascal, if you maintain 7 megapascal, it will increase. The pressure amplitude increases. Finally, at some particular time, the engine may fail. If you maintain 7.5 megapascal, then the pressure fluctuation will be constant. It will continuous, and engine fails at some point. The performance of the engine may decrease. The engine will go for underperformance. Okay, so this is about instability, bulk mode of instability in liquid and solid propellant rocket motors. So for coming to the summary of today's lecture, we have gone through the combustion instability. What is combustion instability? How it affects the performance of a combustion instability, and also we have gone through the different reasons for arising of combustion instabilities. We have gone through the real world examples that arise in the developing stage of engines, combustion instabilities. Okay. Next, we have gone through the bulk mode of instability, wave mode of instabilities, and how this affects the combustion chamber performance. And also, we have gone through the modeling of bulk mode of instability in solid and liquid propellant rockets. So, this is about today's lecture. Thank you.